Hello everyone, welcome to my presentation that will cover creating shaders for video games. Shaders can be a difficult topic to tackle on your own, so today I will try to introduce them to you in a brief and a short way so you can have a starting point to explore them at your own pace. So let me introduce myself first. My name is Felix Sumpon-Pagdi. During college, I studied software engineering, and after graduating, I've worked in a few software and also game development companies. In 2018, I started teaching at LaSalle College, and around the same time, I also started my own game development company, which is Gel Snow Studio. So let's get started. So what are shaders? Shaders, first of all, they're used in digital entertainment to create special effects. So in places like movies, 3D animations, and very commonly found in modern video games. So simply put, shaders are programs, which means a set of instruction that takes an input and creates a result. You can have vertex shaders, which will produce 3D information, so for example position for vertices, and you can also have pixel shaders, which will produce information about colors for 2D pixels. Here it is a screenshot of Minecraft, which shows to you the effect of shaders being applied. So you can see that there's a significant visual difference between both before and after screenshots. Shaders are very powerful, but they also come with limitations. So to be efficient, shaders run on GPU threads, and these threads have important restrictions. Two important ones are that they're blind and memoryless. So what this means is that one thread has no information on any other thread. So they are all independent from each other. And it's also memoryless, meaning that after a thread has done this computation, so for example, it draws the color red, and its next cycle, it has no memory of what it drew the last time. So it doesn't remember that it has drawn a red pixel. This may seem difficult at first to overcome because in everyday programming, you're able to access any variable or store values in memory and access those to perform your tasks. But in shader programming, these are two important limitations that will change the way that you think about problems and how to solve them. So for today, we'll use three different platforms to illustrate shaders to you. This is interesting because if you maybe search on the web for how to learn about shaders, you may be presented with only one platform and they will focus on that. But being able to look at shaders on a multiple platforms will give you a very strong overview of how everything uses the same notions. So as you learn how to use shaders in one platform, you'll be able to use it in other ones easily. So first we will start with Shadertoy, which is an online shader editor, and then the other two are game engines, and they're both taught at LaSalle College. Unity and Unreal Engine 4. Okay, so I will now open Shadertoy on my browser and continue the lecture there. Here. This is the interface for Shadertoy. So when creating a new shader, on the left you have a preview of the result of your shader, and on the right you have the shader code itself. Let me briefly explain the code here. So this function takes an input and an output. The output is frag color, which is the color of the fragment, the pixel basically. And the input is the coordinate of the pixel. So given a coordinate of a pixel, the function requires you to pick the color for it. So the default code here that generates this animating color is a little bit complicated, so we'll simplify it first to be able to understand what's going on. What if we don't assign anything to frag color? What will happen to the output? Let's try it out. What if we just simply comment the whole code here? Then I compile with Alt plus Enter. Okay, so the result is completely black. Let's try to make everything red now. How is it going to work? Okay, so let's see. In the first line here, we normalize the pixel coordinates, meaning that the input frag coordinate here is dependent on the resolution of the screen. So for example, the pixel in the corner here could be 800, 600, right? 800 in X, 600 in Y. To simplify our calculations, if we divide the coordinate of each pixel by the maximum resolution, then we constrain the range of values for the coordinates between 0 and 1. This is exactly what we do here. So we would divide the coordinate of the pixel by the resolution. This notation here, .xy, converts a vector of dimension 3 or 4 into a vector dimension of 2 dimensions. Because frag coordinate is a vector of 2 dimensions, it needs to be divided by a vector of also 2 dimensions here. Okay, so now we have UV, which is the coordinate of the pixel but normalized between 0 and 1. So our output here to the screen, if we want to output red, then we simply need to pick 1 and 0 and 0 and 0, like this. Because you remember that the structure for the color of a pixel is RGBA, red, green, blue, and alpha. So it doesn't depend on the UV yet. The position of the pixel on the screen doesn't matter because we want to draw everything red. Okay. So then it means that this UV, we will use it a little bit later. So now what if we want to animate things a little bit? What if we want to go from black to red and back to black? So like a blinking red light. This is also done easily through the use of time, sign, and absolute value. So first, let's create a local variable here to simplify our code. Float red. So iTime is a variable that increases over time. What can we do with this? Well, if you use the sign function with this and using time as input, then you will receive a value that fluctuates between -1 and 1. So if you want something between 0 and 1, then we just need to use the absolute value here, ABS. If we use all of this inside my vector 4 here, then we receive the result that we wanted here. So we have time that's increasing, sign that keeps this between -1 and 1, and then you have the absolute value that keeps this between 0 and 1. Then you have an animating red light. Okay. Let's move forward in our notes here. Okay. So let's go back to the UV now that I talked about earlier, because this will be important for sampling colors from a texture and displaying it on the screen. Can we display the coordinates of a pixel on the screen? Yes, because every pixel has different coordinates. We can use those coordinates and the color of the pixel. So we could use maybe the X coordinate for the red value and the Y coordinate for the green value. So let's give this a try. I'm going to erase this code here. And here I will put uv.x and uv.y. So remember here that this is red and this is green. Let me compile with Alt-Enter. Here. Now every pixel on the screen has a different color. Can you determine where is 0, 0? Yes, because 0, 0 would be 0 red and 0 green and 0 blue. So that means black, right? So black is right at the bottom left here. So it means that here, this is 0, 0. What would this be then? So look at the color. This is red, right? So red is 1 for the red value of a pixel and 0 for green. So it's coordinate 1, 0 here. Then green would be 0, 1. So what's yellow? Yellow would be 1, 1 because yellow is fully red and fully green. 1, 1. Okay. So now, how do we use this to map a texture onto the screen? Well, first, we need a texture input, right? So, on this website, you can have different inputs in these channels at the bottom of the screen. So if I click on I channel 0 here, I'm able to choose a texture. So let me choose an input texture provided to me by the website. One second, I think it's loading. Here. Let's pick London. Okay. So by using this UV coordinate, I'm able to say, okay, hey, on the bottom left here, you're a pixel at the bottom left of the screen. So could you check in the texture here and fetch the color that's on the bottom left of this texture too, and then draw it on the screen. Same thing with the other coordinates. You're at 1, 1 because you're yellow. Well, go get the texture at 1, 1 here. So then we will be able to display this image on the screen here. So we do it like this. First, we go and create a text variable like this and use the texture function to be able to get the color of a pixel on the texture itself, following the UV map. Sorry, the UV coordinate. So the first parameter here is the channel on which your texture is on, and the second will be your UV coordinate. Okay, then here we do this. Oh, sorry, this is a vector 4, not 2. Simply, you assign the texture to the frag color, and this should do it. There you go. So now you may ask, this seems quite straightforward and simple, and you might not really see the use of going through all of these UV calculations. Well, what if we wanted to modify how this texture is displayed a little bit? What if I wanted to flip the whole texture around? So I wanted to draw this pixel that's on the bottom left on the top right instead, and I wanted to draw the top right pixel on the bottom left, and the same for every pixel on the screen. Well, this will be easy if you understand how the coordinates, the UV coordinates, can be modified by calculations. So if I want this to be 1, 1 and this to be 0, 0, I simply apply a 1 minus x calculation on each of these coordinates, because 1 minus 1 will give 0, so here will become 0, 0, and 1 minus 0 gives 1, so this will be 1, 1. What about these here? Well, this will also flip. This 0 will become a 1, this 1 will become 0, and this 1 will become 0, and this 0 will become 1. So every pixel will be flipped here. Let's give it a try, okay? First, let's display the UV again. I'd like to see what happens to the UV first. So let's do something like this. Okay. Okay, so back to the UV. Now I apply my 1 minus function like this. Make sure that this is a vector 2, because UV is a vector 2 also. Whoops. Like this. So you see now, black went to the top right, yellow went to the bottom left, and green and red has also flipped. So every pixel has moved around now. Okay, let's see if we reuse this to sample the texture, what will happen? Let's try it. So make sure to move it before the texture sampling code here, like this. There, exactly what we want. So the whole picture has rotated 100 degrees, 180 degrees essentially. Okay, hopefully you start to understand now the use of UV manipulations. Okay, so let's do one last exercise on this Shadertoy platform. What if we wanted to desaturate the whole picture, meaning that I'd like to turn it grayscale. This then will be done through a manipulation of the colors themselves, because the desaturation formula is to add all colors of a pixel, so red, green, and blue, and take an average of them. So you do R plus G plus B and divide by 3. Okay, let's give it a try. And then this value, give the result value to every pixel, because that's how you obtain a grayscale color, by having the R, G, and B component all be the same. Okay, so let's try that. Float value is equal to text.r plus text.g plus text.b divided by 3.0. Okay, and then we can do like this. Make a vector 4 out of this value. Done. So this notation here, when you try to create a vector 4 and you send it only one parameter, it will simply copy this parameter for every elements and for the vector. So if it's a vector 4, it will copy this 4 times. So there you go. You achieve the simple desaturate effect. Okay. So let's move on to Unity now. For Unity, I'll show you a real use case for shaders for the game that I developed named Metal Unit. In my game, there are plants, and I achieve a swaying effect for the plants, so meaning they kind of swing left and right on the screen. It's a very simple shader, but the effect is quite interesting. So I will show this to you now. Okay, we're in Unity now. So inside Unity, you can create a new shader by doing a right click, going in create, shader, and I will choose an unlit graph here. Unlit, because I don't want my shader to be affected by lighting. I will do a simple pixel 2D shader, and graph, because I want to use the shader graph system in Unity. So shader graph is a visual shader editing system. Visual editing tools are very useful because they allow you to preview the results node by node, and also it does not require any programming knowledge. So for artists, it's a very interesting tool. Okay. So our first exercise should be to recreate the red blinking shader before starting to work on the plant shader. Okay. So what did we have for the red blinking shader? We had a time node. So what's convenient here is that the time node already has a sine time output. So I don't need to add my own sine node here. I can simply use sine time, and all that I need to add is the absolute value. Okay. Next, I need the make vector 3 node, because this will allow me to take the output of this blinking white light and instead make it red and assign this to the color output. So there you go. We recreated the blinking red light. So you can already see how your knowledge from the Shadertoy practice can be applied to something different, like in Unity. Okay, so now let's get started on the plant shader. First, I'm going to use a plant texture to sample the color on it. Okay, so by clicking the plus here and choosing texture 2D, I can have a input texture here. Okay, so let's pick this plant here. All right, next, by dragging this node in here, I'll be able to use this as an input, and then I search for the sample texture 2D node here. Okay, and then I connect this to the texture, so here, and then I connect the color node to the color node here. Okay, so this preview here is spherical, but I'd like to see this on the plane, so I click on quad here. Now I see my plant. Okay, what we're going to do next is modify the UV coordinates, because we want the plant to move left and right. So we need to try to offset the X UV coordinates over time. Okay, so as I said, we need the UV node. So let's go and get the UV node here. This provides to us the default UV coordinates. So 0, 0 at the bottom left and 1, 1 at the top right. We can then use a split node here to split X and Y coordinates, so we can affect them differently. I want to affect the X coordinate because that's where the offset needs to happen. So what if I simply add time to it? What will happen if I add sine time to it? Let's try it. So I take X and I add sine time to it. What's gonna happen? And now I recombine the X and Y value together into a vector 2, which is the input that's required by the sample texture to the node. Okay, let's make a vector 2 again, like this. Ah, there we go. Interesting. So the plant now is shifting left and right. Y, like the Y coordinate, has not been modified, so nothing changes in the Y mapping. Because we add a value of sine time into our X coordinate, well, it shifts its mapping left and right. When it goes to -1, it goes out of the screen to the left. When it goes to 1, it goes out of the screen on the right. Okay, interesting. Next exercise. For the plant shader, we want the plant to be mostly mobile at the bottom of the plant because it's stuck to the ground. And it's mostly the upper leaves that are like swaying, right? So how can we accomplish this? Well, if you think about the y coordinate, it's 0 on the bottom and it's 1 at the top. And everything in between is a constant rate. Alright, so it's 0.5 in the middle. So what if we multiply this y coordinate to our time offset? Is that going to work? It should, because it's 0 on the bottom. So then the offset multiplied by 0 will give 0. And it's 1 at the top. So then the offset has its maximal value at the top. Okay, so let's add a multiply node. Let's multiply this offset by the y coordinate and use this instead. Oops. Sorry. Let me fix this. Like this. There you go. I did a small error in the connections there. Okay. So the multiply node comes right after the time node because that's what you want to make sure that it's 0 at the bottom and 1 at the top. Okay. So there you go. So how do we improve this now? Well, the swaying is a little bit intense, like it goes out of the texture. So let's try to limit it. So we want to limit this offset by multiplying it by maybe a value less than 1. So maybe 0.25 maybe. So I need another multiply node. And I need to give it a value less than 1. Okay. There you go. Now the plant is swaying left and right with less magnitude. There's one last polishing task that we can achieve here. Because now the plant sways left and right at the constant magnitude increase on its height, right? So in the middle it's swaying at half strength, and at the top it's swaying at maximum strength, and everything is like uniformly increasing. But plants don't really do that. They curve, right? There should be a curve in this the swaying. So how can we achieve this? Well, the problem lies in our y coordinate. Again, this increases at the uniform rate. What if we use a power node here to make it such that values at the bottom here are a little bit smaller than the values at the top? Okay, meaning that the values at the bottom here are closer to the bottom than the values at the top are close to the top. Okay, so in our y coordinate here, instead of using this directly and multiplying it to our time offset, then we will use a power node. Power. Okay, so I will drag this away a little bit like this. So it will take the power of 2 of the y coordinate and then multiply this to the time variable. Ah, there you go. You see, you've achieved a curving effect now for the plant, and this is the final result that we use in my game. So what does it look like in this sample scene that I created just to showcase this shader here? Well, it looks like this. It has a quite interesting effect. Okay, so now let's finish this presentation by taking this example and showing to you in Unreal Engine 4. Okay, so now we're in Unreal Engine 4. I've opened the material editor, which is the equivalent of shader graph in Unity, so it allows you to create shaders. In Unreal, it's much more mature since the game engine has been around for a longer period of time, so the developers had time to improve this system a lot. So here we have a 3D mannequin, and currently the shader is simply sampling the beige texture on it and applying it to the model. Let's try to see if we can affect this 3D model in an interesting way by reusing what we learned from the plant shader. Can we make the mannequin sway? Let's give it a try. Alright. So we see here there's a world position offset node. So this will allow you to manipulate vertices of a mesh. So points on this 3D model. I'd like them to be swayed left and right. So let's give it a try. Okay. So let's take a time node again and connect this to a sine node. So this will allow us again to have a value that changes from -1 and 1. So can we create a vector 3 now? And use this -1 to 1 range on the x-axis and use this for the offset. What will happen? Ah, there you go. So that character is swaying left and right, exactly how our plants did the first time, right? So now can we improve this effect a little bit by, again, making it only sway at the top? Yes, by using a world position node. So before, we had to rely on the UV of the texture, because at the bottom the UV was 0, and at the top the UV was 1. Well, similarly for a mesh, if the feet of this mannequin is at 0 height, we can multiply this z coordinate to be able to keep the bottom here mostly stationary by having its offset be close to 0. Okay, so let's go get the world position node. I will multiply it by a small value because I don't want the sway to be too big. So I will multiply this by something arbitrary like 0.25. We will break out the components here because I only want the height of this. So I want to break this into 3 and use b. So for elements of a vector, sometimes they call RGB, but they also mean X, Y, and Z. So Z in Unreal is the height, so I will use the height here and simply multiply this to my sine output. And let's see what happens. Like this. We've achieved the effect. What if I want to add a little bit of curving to this? Well, again, you simply use the power node and affect the offset before it's being multiplied here. So power, and just add this here and connect this to this. So this will make values closer to 0, much closer to 0, where values close to 1 will stay close to 1. So there you go. Now you have a funny mannequin swaying left and right. So what did we learn here? Well, you've seen that logic that you've used in a 2D environment on a 2D texture sprite, well, can be applied to a 3D mesh after you do a few adaptations. So instead of working with UV, now we work with world position, and instead of picking a color on a different part of a texture, we affected vertices on a mesh. We just offset them now. Okay, so that will be it for the presentation. I hope that you've seen that, you know, even when working with different platforms, Shadertoy, Unity, and Unreal, you're able to apply knowledge that you've acquired from one platform on another one quite easily. And we've been able to create these interesting effects in a short amount of time. One of them, which is a plant shader that's used in my game. And all of these topics can be covered at course at the La Salle College during game engine courses, programming courses. Just mention it to your professor and they will be happy to show this to you. Okay, thank you, and I hope you enjoy the rest of Tech Week.